the Poisson process.
Conditions defining a Poisson process. A Poisson process is a description of events that occur randomly over time. It's a model for random occurrences of events over time or space. Things like calls on a telephone or computer network, internet connects, and so on. Points in space or time. So for example, down below we have a picture of some points at the point X occurring along a time axis between 0 and 10. And there are three properties required for the Poisson process to be used. The first is the independence property. The independence property says that if we count how many events there are in two different time intervals that are non-overlapping, those counts, those random variables, are independent of one another. In the figure, you'll see two different intervals. We've counted how many events occur in each of the two. In this one random occurrence of the process, there happen to be two in one interval and I guess two in the other. In any case, those two counts are independent because the intervals are non-overlapping. The second property is individuality. This says that while the probability of one event in a small interval is relatively small, the probability of two or more events in such a small interval is smaller still. Indeed, if the interval is of length delta t, where delta t is small, the probability of two or more events in the interval from t up to t plus delta t is what we refer to as little o of delta t. Little o of delta t is referred to as the order notation. It stands essentially for a quantity which is so sufficiently small, let's say it's g of delta t, it's sufficiently small that when I divide by delta t and then let delta t go to 0, the ratio of g of delta t divided by delta t also goes to 0. In a sense, that means that g of delta t is smaller than delta t, vanishingly smaller, as delta t approaches 0. So we're saying the probability of two or more events in a small interval is considerably smaller, vanishingly smaller than the length of the interval. The third property is called homogeneity. Events occur at a random and uniform rate lambda over time, which means that the probability that one event occurs in an interval of length delta t is lambda times delta t. It does not depend on where the interval is placed in time. It doesn't depend on the value of t. It's a multiple of delta t. However, once again, this is not the exact probability, lambda times delta t. There is an error term which is little o of delta t, an error term which goes to 0 faster than the delta t does. So wherever we are, whatever the value of t, the rate at which events occur, lambda is the same. There's a theorem which says that whenever these three conditions, independence, individuality, and homogeneity, are satisfied for a process, then we can refer to this process as a Poisson process. If we count x, the number of events in a time interval of length t, units, then x will have a Poisson distribution with parameter mu equals lambda t. It's the rate parameter times the length of the interval. Here's an example. Arrivals at the math C and D. Suppose students arrive at the math C and D at random, at an average rate of, say, one student every 5 minutes. And they arrive according to a Poisson process. We're asked to find several probabilities. First, at least 2 students arrive in an hour. Second, that no customers arrive in the next 2 hours. And third, that 3 students arrive in the first hour if we know that 10 students arrive in a 3-hour period, the first 3-hour period, say. Solution. Let's first look at the probability that at least 2 students arrive in a given hour. Let x be the number of students arriving at the math C and D in a 1-hour period. Here, t, the time interval of interest, is 1 hour, or 60 minutes. The rate of arrival is 1 over 5 students per minute, because we were told that students arrive on average every 5 minutes, or approximately 12 per hour, or 12 per 60-minute period. Then x has a Poisson distribution, and the parameter mu is lambda, 1 over 5, times t, 60 minutes. 1/5 times 60 is 12. The probability at least 2 students, the probability x is greater than or equal to 2, can be obtained by computing the probability x is less than 2 and subtracting from 1. 1 minus f of 0 minus f of 1, or 1 minus e to the minus 12, 1 plus 12, that turns out to be 0.9999. It's very, very, very likely that at least 2 students will arrive in a given 1-hour period. B. No customers arrive in the next 2 hours. That seems indeed to be very unlikely. Let y be the number of students arriving in a 2-hour period. This is 120 minutes. So now the parameter mu is lambda 1/5 times t, which is 120. Y has a Poisson distribution with mu equals 24. The probability y is equal to 0 is e to the minus mu, e to the minus 24, which numerically works out to about 3.8 times 10 to the minus 11. This is infinitesimal. And finally, for C, what's the probability that 3 students arrive in the first hour if we're told that 10 students arrived over a 3-hour period, including that first hour? This is a conditional probability. We need to define 2 events. A is the event that 3 students arrive in the first hour, and B is the event that 10 students arrive in a 3-hour period around that. Then we've been asked to obtain the probability of A given B. Probability of A given B is the probability of the intersection A intersect B divided by the probability of B. The numerator is the probability 3 students arrive in the first hour and 10 students arrive over a 3-hour period. What does that mean? It means that 3 students arrived in the first hour and 7 more in the next 2 hours. We've expressed it this way so we can exploit the independence property of the Poisson process, since the first hour is independent of the next 2-hour period. So the probability of 3 students in the first hour and 7 in the next 2 hours is the product of those 2 individual probabilities, hence the numerator. The denominator, of course, is just the probability of 10 students in a 3-hour period. We've already seen the parameter for a 1-hour period is 12, and so 3 students in the first hour has probability e to the minus 12, 12 cubed over 3 factorial. 7 students in the next 2-hour period, the parameter now is 24, so that's e to the minus 24, 24 to the power 7 over 7 factorial. 10 students in 3 hours over a 3-hour period, the parameter is 36, mu is equal to 36, so I get e to the minus 36, 36 to the power 10 over 10 factorial. When you work this out, it becomes 10 choose 3, 12 over 36 to the power 3, 24 over 36 to the power 7. It looks familiar. In fact, it's a binomial probability. The Poisson process applies to events that can occur over time or space. These events could refer to, say, bacteria in a volume of water, or insects in a tree, or weeds in a plantation. Here's an example. Suppose bacteria are immersed in contaminated water at an average rate of lambda equals 2 per 10 milliliters of water. What's the probability that a 30 milliliter water sample is free of bacteria? Or, the complement, what's the probability that there's at least 1 bacteria in a 30 milliliter sample of water? Here, the count of interest is the number of bacteria in 30 milliliters of water. The parameter for this Poisson distribution is the rate, which is 2 in 10, 2 over 10, times the size of the sample, 30. 2/10 times 30, the parameter mu is equal to 6. So x has a Poisson distribution with parameter 6. And the probability that x is greater than or equal to 1 is equal to 1 minus the probability at 0, which is 1 minus e to the minus 6. That turns out to be 0.9975, very close to 1. Now once again, there's an extremely high probability. We're almost certain that there will be at least 1 bacteria in a water sample of 30 milliliters. These distributions, the binomial and the Poisson, can be combined in various ways, and we'll provide a couple of review questions along these lines. First, suppose calls to a helpline follow a Poisson process, and the average rate of calls is 6 per hour. Our operator likes to take 10-minute breaks, and indeed takes 8 10-minute breaks during the week. What's the probability that in 3 of these breaks, there was exactly 1 call, which went, in this case, unanswered? The second question is, find the probability that in a given 20-minute period, which has more than 4 calls, there are exactly 10 calls. This is a conditional probability calculation. Given that there are more than 4, what's the probability that there are 10? For the first part of this question, let's look at the probability of exactly 1 call in a 10-minute break. Let y be the count, the number of calls in a 10-minute break. Y has a Poisson distribution with parameter which depends on the rate, 6 per hour. So on average, in a 10-minute break, we expect 1/6 times 6, or 1 call. So mu is equal to 1. Therefore, the probability that y is equal to 1 is e to the minus mu. Or e to the minus 1, let's call that for now p. Now in this question, we wanted to know the probability that a certain number of these breaks had exactly 1 call. Let's let x be the number of these 8 breaks which have exactly 1 call. Each break can be considered to be the trial of an experiment. A success is defined to be a break with exactly 1 call. Probability of a success on any one trial is the value p, or e to the minus 1. And what we're asked for is the probability that x is equal to 3. This is a standard binomial problem. X is binomial with parameters 8 and p. We're asked for the probability that x is equal to 3. Therefore, that's 8 choose 3, p to the power 3, 1 minus p to the power 5. And substituting p equals e to the minus 1, we obtain 8 choose 3, e to the minus 3, 1 minus e to the minus 1, all raised to the power 5. For the second part of this question, let's let x be the number of calls in a 20-minute period. Now x has a Poisson distribution with parameter mu. Mu is the length of the time interval, 20 over 60 in hours, times 6 calls per hour, so the parameter mu is equal to 2. We're asked for the conditional probability that x equals 10, given that x is greater than 4. That is, of course, the probability x equals 10 and x greater than 4, divided by the probability x is greater than 4. But the numerator, the probability x equals 10 and x greater than 4, can be replaced by the less redundant statement, the probability x equals 10. So if we let f of x be the probability function of the Poisson, then the numerator is f of 10, the denominator is 1 minus the probability x is less than or equal to 4, so we add up f0, f1, f2, f3, f4, and subtract from 1. Here's a second review question that you can try on your own. Probability of winning a prize in a school raffle is 0.05. If a particular class distributes 100 tickets, what's the probability that there are exactly 2 winners among the students in that class? You can do this using the binomial distribution, but you can also try the Poisson approximation to the problem and compare the 2 answers. You will discover that the binomial and the Poisson give similar numerical values. Because in this case n is fairly large, 100, p is reasonably small, 0.05.